I've sketched an intuition for how we assign types to expressions, but let's turn that into a type checking function. And we're going to write our type checking functions not in Plait at first, but in this other traditional notation for writing the type checking function. So here, the name of the type checking function is colon. The part on the left, that's the input to the function, and the part on the right is the output of the function. So this type check function, when you give it any number expression, is going to return the type num. And if you give this type check function the t true expression, it's going to say bool, and for false it will also say bool. Now over here we have a more interesting case of the type check function. And you read these upside down. You read the bottom part as the input to the function, and the right part as the eventual result of the function, but this result you only get out if you can make these other recursive calls to type check and get these other specified outputs. So this says that a plus expression has type num if you take that first expression and type check it, and it has type num, and you take that second expression and type check it, it has type num. Right? So that's the conditional we had intuitively sketched out before, here effectively sketched out in code. Right? So again, it says plus has type num if these two recursive calls produce the values that we specified. So we can try calling this function on explicit expressions like 1 or true, and based on these definitions of type check, we'll get num and boolean in that case. If we say 1 plus 2 and we call the type check function, we will get num. And if we trace this type check function, that's what we're showing in this tree here. We're showing that a trace of making the recursive call to type check on 1 will give us number, and a recursive call to type check on 2 will give us number, and that will justify getting num out as the result at the end because that's consistent with this rule up here. Right? So another way of saying it is with this input, we can sort of match this tree to that specification of the type check rule. If, on the other hand, we had plus 1 false, and we try to do that matching, it doesn't work out. Because we have plus 1 false, we make a recursive call on 1 and get back number. We make a recursive call on false and we get back bool. And now we have num and bool, which does not match this pattern, num and num. Therefore, we can't put num at the bottom here. And again, when I write no type, that doesn't mean we return no type. It just means we can't make the tree. The trace doesn't work, so this expression has no type. We can make bigger trees, so if we start with the input plus, and then plus 1, 2, 3, then we make the recursive call on plus 1, 2, and we've already seen how that subcomputation go. Eventually that justifies the result num. Meanwhile, 3, we make a recursive call to get a num, and now once again, just looking at this line, we're able to match it up with this line, because we got num and num for the two expressions, and so we're allowed to put num as the result down there.